Our final application will be lifting problems. So we'll start by drawing a y-axis in the vertical direction and choose a convenient origin. And we'll assume the interval a to b corresponds to the vertical extent of the fluid. For y between a and b, we'll find a cross-sectional area, a of y, of our horizontal slices, and the distance d of y that the slices must be lifted. So our work required to lift the liquid in general is the integral from a to b of rho, which will be the density, times g, which is gravity, times a of y, d of y, dy. So let's consider a cylindrical tank with a height of 10 meters and a radius of 5. We want to know how much work is needed to pump all the water out of the tank. And the water is pumped to an outflow pipe 15 meters above the bottom of the tank. So this is a cylindrical tank. And we'll say that the bottom of this corresponds to y equal to 0. Since it has a height of 10, the top will be equal to y of 10. So one of the first things we need to know is a of y, the area of a cross-section. And these cross-sectional areas look like circles. So the area of a circle is pi r squared, and we know the radius here, which is 5, so we have 25 pi. D of y is the distance that it must be lifted, and that's going to depend where we're considering. If we start at the top, we'll have to lift it 5 meters. If we start at the bottom, we'll have to go all the way at 15. So we can do 15 minus y. So we're going to integrate from 0 to 10, since that's the height of our tank, of the density, which the density of water will be 1,000, times gravity, which is 9.8, times a of y, times d of y. We can move these constants out front. So 1,000 times 9.8 times 25 pi times the integral from 0 to 10 of 15 minus y dy. So this will be 1,000 times 9.8 times 25 pi times 15y minus 1/2 y squared, going between 0 and 10. So when we substitute this in, 1,000 times 9.8 times 25 pi times 15 times 10 minus 1/2 10 squared minus 15 times 0 minus 1/2 0 squared. And this gives us 7.697 times 10 to the 7th.